Okay guys, happy Friday. So today we're going to go through some of the practice examples of applying VTNA. So we'll talk a little bit more about some of the theory, what it sort of looks like. I've got some examples of how you would do data handling. I've shared with you guys a VTNA template and a data set. Did you guys get those, at least on the Canvas site? Ideally, if you got your laptops, bust them out, download both of those tools, get them open in Excel, and we'll work through those ones live. So, as I mentioned last time, the goal of applying VTNA is this overlay kind of analysis. What you're going to do is take a matrix of reactions for a mechanism you're trying to interrogate. You're going to take initial conditions of individual components. So in this case, we're interrogating the potential order of A, B, and catalyst. And if you look at this grid, you can kind of find a pairwise comparison where only one component should have been changed. That way we can start to work through and solve orders in each. Again, from a high level, I'm happy to go through the math in more detail, but just in terms of conceptually, all you're doing is you're creating this novel, what we call a modified x-axis, the time axis down here. And what we do in that equation, the goal here is to say, I have the ability to multiply or divide or normalize the impact of the variable that I'm trying to perturb. In other words, I will change, in this case, I am checking experiment 1 versus experiment 2, so blue versus yellow. In that pairing, I only change the initial concentration of A. So if you look at this first one here, where you've set the exponent to the component you've changed, in this case, the exponent to A to 0, that's equivalent to your normal time course plot. That's the unperturbed, true concentration of product versus time axis. So remember, anything raised to the power of 0 equals 1, right? So basically what we're saying is that the sum error, or the impact of A raised to 0 is irrelevant. You're looking at just the normal time axis in that point. So if you look at this one here in this bottom corner, there is a difference between the two. The yellow curve of product and the blue curve of product do not overlay. We expect that there's an order in, you changed A, product rate doesn't look the same, probably has an order in A. That's the first sort of qualitative piece that you can get. In order to get the numerical value, what you're going to do in that sheet is we're going to change this value, the constant. And what that's going to do is basically squish and stretch the time axis, normalizing for whatever this component is on this x-axis. So in the case of this particular graph, since we're trying to solve for the order in A, I'm using the graph where the math is set up to deal with variations in concentration A. I'm manipulating the order in A, and a result of that, if you look left and right, I try a value of 0.5. The curves get closer, but they do not overlay yet. It is not half. If we try 1, the two curves interleave with each other. That's a really good overlap. Order of 1 looks solid. If you go higher than that, what you start to see is he breaks this overlap again. So really what we're doing here is you will set up this in your sheet. You will put your data into the proper sort of template. What matters is you're going to be taking the product concentration and your reaction concentration. They have to be on the right graph for whatever experiment you're interrogating, because there's going to be different x-axes or different product axes depending on what you're trying to visualize. But once you've got that set up properly, the way I solve for order in A is I use a reaction where I have varied A. I manipulate the power constant for that component A. I just index it. I change it larger and smaller. And I just look at the result and say, oh, 1 looks like the best overlap. That's kind of hunt and peck it that way. Does that conceptually make sense? Right? What you're doing is this. Right? So I can walk you through the math of how that overlap is. What you're functionally doing is saying, if I can compensate for the rate of change of A in both of these two, I can equate one rate with another rate. That's what you're doing between those two. And as I index or change the power, this exponent to this component, I will eventually walk all the way through from when it's equal to 0, that's just your normal concentration time profile. As I increase the number, the value of this, you'll see the two curves actually start to intersect. They actually cross, and then they reverse. So what you're looking for is find one value where everything overlaps as best as it can. This graphic was provided by an amazing graduate student, Finn. He's the one that sort of created this whole point. I like this visualization. You're just doing, you're going to be doing this one at a time, but he's showing you the full movie, what would happen as you index this value here. So that's how you solve for a single component. What you then do is you go through iteratively each by each. Solving for B requires you to use, in this case, the pairwise component, blue versus green, where A doesn't change, B did change, catalyst is the same. We set up with a different time axis. This time B is the thing you're normalizing against. We're indexing the value of B. Once again, in this particular example series, all of these graphs are actually from Jordy's, the second one right here, this 2016 1608 paper too. But in this case, it's first order in B as well. So 0 doesn't fit, half doesn't fit, first fits. Okay, so that experiment, blue versus green, tells us it's probably first order in B. If we then go through and do the same thing with catalyst, the only difference is the time axis with respect to catalyst, you notice it's time times catalyst as a constant. Now you're making an assumption there where the concentration of catalyst does not change. It's whatever the initial is same all the way through. So the time axis is a little bit easier, but it's just time times catalyst. Once again, you go through and change the power associated with it. Once again, squash and stretch, they overlap. So in this case, you're doing blue versus red, where red has a higher concentration of catalyst, therefore it runs faster. That's why it's completing quicker. And then the overlap just comes from that first order dependency you get. What you can then do is actually, if you want, you can take any two experiments and express them with a multiple normalization. So there's the value I've shown you here, setting up the time normalization. Typically what we'll do is we do this time manipulation with reference to a single variable. So I'm trying to solve for B, so I set up a sheet just to probe for B. I'm trying to solve for A, I set up a sheet for probing for A. But since it's a power series, you could actually set up a sheet that is order in A, order in B, order in catalyst, all in one. So all that is here is you've just made a multiple here where we're actually taking each of the values and multiplying through. So by doing that, you could actually take all of these different data sets, put them onto one plot, and now what you're doing is manipulating 1, 2, 3 variables where what you're trying to do is get a overlap and a straight line. Because what you're doing in this case, if three things could be manipulating these curves, that's what's giving you that curvature and that non-agreement. If I have three different variables, A, B, and cat, I could go through and plot one graph like this and just iterate through A, B, and cat until I find something where all the curves now overlap with each other and becomes a straight line. When you do that, the slope of that line on this graph technically is the observed, the k-obs for that system. The downside with this can be that it may be an oversimplification. For you guys in Hunt and Peck, you're now going to be standing around with multiple data sets going, let's try 1001 or 0.16, whatever. Like you're solving three variables iteratively. It can get tricky. Does anybody know about a tool called Microsoft Solver? A couple? What you can do with a tool like Microsoft Solver is if I score this, let's call the linearity or the R squared, I've got an objective function that says I am trying to find three different values within some range where this line, the best fit line, is both linear and a tight R squared. You can set that up in Excel where you're saying, please go and iterate, try different values of those three different constants such that you find the best fit that gives you the straightest line. I can actually go through a tutorial for how you guys do that. That is what's called, it's a nonlinear regression tool that's actually built into Excel. It does take a little bit of configuration, but it's very powerful. If in this case where you've got three unknowns, you can just ask Excel to do all your linear algebra to find the best value for it. Now the downside again is overfitting. This is just like fitting with Copasi where you're saying, I want to find these three values. If you don't have enough data sets or enough authentic, or call them, non-identical data sets, you may find more than one value or series of values that fits equally well, right? You may see 0, 1, 1 and 1, 0, 0 may all look the same. Yeah?
From experience, fair warning, it will sometimes just nuke your data and call it good because look, the error, it's all zeros.
Yes, again, you have to, this is where you need a light hand and how you set up your function to tell it to do what you want. It's the same thing as, imagine if you gave your experimental conditions over to an algorithm. And you tell this algorithm, go scan conditions so that you find the fastest reaction you can possibly can. And you can vary catalyst, solvent, whatever you want, go nuts. almost every time that algorithm is going to come back and say, run the reaction with 50 times the amount of palladium you'd ever possibly, like run it in palladium basically at the temperature of the sun. So it will give you, like this is poop in and poop out. If you tell the system, this is like the joke about AI, dear AI, please solve all the world's problems and help with the global climate crisis, kill all humans. Okay, no, parameters, right? Like it'll do what you tell it to. So if you say lowest error, just it'll do something dumb and blow it up. So you do have to be careful. Anyway, if you want, this is a tool that we created in the lab called Kinolite. The website is still live. This was an ArcsIV, a Chem archive paper that Finn built out that talks about a very simple web-based application for you to drop in your data and it'll do the fitting automatically for you within anything with a value of 0 and 2. So if you don't like what we're going to talk through today in terms of using the Excel sheets, this is a simple way for you to just drop your concentration versus time data into it. There's a sort of a README file of how to actually submit things. It can be helpful for that point. One part I want to mention, though, is as you're doing your fits, remember that when we graphed this part before, if you have a system like we've shown here, this is the one we've sort of talked about before, where your forward and backward rate constant here is not super product favored. It is still product favored, but it's still only sort of a 10. And then the rate determining step, the second one here, has at least the similar rate constant as the reverse for this first one. This is one of those kind of middle cases where one step is not massively faster or slower than something else, so that as you change the concentration of A, you are going to get different behaviors in the order of A, right? This is something where at very high concentrations of A, it will appear zero order because this will be saturated, but at low concentrations of A, the retro constant and this constant are starting to dominate, so you're going to start to see some sort of first order type behavior in A. So the mention here is that if you go through this, and I do a pairwise mention of these two high concentrations in A, so 1.5 and 1, where I hold catalyst constant, that's what this one looks like, and you can see the order in A for my VTNA method looks close to 0, it's 0.18. So we're not fully saturated, but it's also not fully first. We're somewhere in between. If I take these lower two concentrations, 0.2 and 0.4, now I do that, I still get an overlap. The order between that binary pair is 0.6. So if you've ever, in the previous lectures, where I've shown you a plot that shows, let's say, order as a function of concentration A, this is how we end up doing it. I would take multiple individual binary comparisons. I check two experiments where that binary comparison are close to each other. So I take 1.5 and 1, and then I take 1 and let's say 0.8, and then 0.8, and then 0.6, and I walk my way down. Each of those binary comparisons can give you an order in A, and then what you do is you plot the observed order of A for VTNA for that concentration range. And this is where you get those sort of like Michaelis-Menten kind of plots, where as you change the initial concentration of A, there's an observed rate or an order, the dependency according to it too. Make sense? So you can do this empirically, basically. One thing I want to flag, what do you think would happen if I took initial concentration A 1.5 and compared it to initial concentration 0.2? So I do a massive jump instead of this kind of slow, like this small binary comparison. But what do you think the data would show you if you took 1.5 versus 0.2? Let me sketch this out. So if I'm saying the order was on the y-axis, the initial concentration of A is on the x-axis, and what we've just said for the system, order starts pretty low when we're in this high concentration regime. And roughly we could say it maybe has something like that behavior. It's got this increasing behavior approaching order equals 1 as we get to lower concentrations of A. And this is done by taking two experiments on either side of this data point, and we're sort of averaging between the two. Right? That's how we make this plot as we walk down. So what might happen if I took this experiment, the super high concentration experiment, and that super low concentration experiment, and I asked it to find the order? What do you think I'd get?
Probably not make any sense. My guess would be that you would get like overlap, but only on maybe
Okay, so you're saying, I think I understand what you're saying. If you drew concentration product against, let's say, my delta time axis where I'm normalizing for the concentration A to some power, right? High concentration of A looks like that. You got lots of A, so you get lots of product. By default, if I'm running it way down here, I'm going to run through a smaller concentration range. And if I have less A, I can make less product, right? So this is not going to look like this. It's going to be down here somewhere, like that. If this was just my normal concentration versus time profile, does that sort of make sense to everybody, right? So if you were to take those two, massive difference between them, and try to fit it, I think you could probably find a value where these start to overlap with each other. What you'll start to see as you start to practice this region right here, where there's no further change, if there is 0 A or very little A in this time, and I put any power here, what you'll see is all of these will all compress almost to a single dot. Because remember, what you're doing is you're squashing and stretching the constant time axis, normalized by how much A is there. If A is almost 0, it's going to pack together, right? So all this tail will suddenly crush together over here. But what it also means is you're taking this small portion of the curve and you're trying to fit all these data points against what might be 1 or 2. So you might still get an overlap, you're right. What will happen though visually, and this is something that you can play with both with Copasi and with the sheets I've given you, it's going to be confusing. What you'll visually see is something where you'll have a graph, you'll have like data point, and you're going to have this buttload of data points that are just kind of crammed together. It gets hard to make a decision of is this a good overlay or not, because you kind of have 2 measured data points usually from your high concentration, and you've got all the data points somewhere in between, so it's kind of like, is it overlapping? Well, I don't know. So that's one, is the data gets hard to interpret just because of the massive difference in data density between those 2 curves. That's correct. But generally what you're probably solving is the average, right? If you could get the overlap to do, really this is the same thing as taking an instantaneous rate versus a global rate, right? If I was just to take a concentration versus time profile and I was going to say a small bit of time and a small change in concentration, I get the tangent of that curve, right? But if I take a very large jump in time and then the corresponding large jump in concentration, I say what is the rate between those two? The slope is just going to be an average between those 2 points, right? It's like taking this curve and saying, what is the slope if I take only this point and this point? I'm going to get a slope that's kind of cutting it off. It's like low fidelity. So you'll still kind of get this idea, but instead of having any curvature, you're just going to get some weird middle average. That's the biggest problem. So yes, I think data is hard to solve, but your resolution drops effectively. This is the same point, the math that Jordy shows in that paper where he called it, what is the order of an experiment? That's the analytical answer where the gap between experiments, the binary comparison, is effectively super, super small. If you took millions of experiments where I tried A equals 1.5 versus 1.4 versus 1.3 versus 1.2, and I do each one of those binary comparisons, I will still get this curve, but it's going to be nicely smoothed, right? You just get more data points along here and you get the full shape versus something that's a little bit more blocky, right? That's all. It's just the resolution of your curve. Okay, let's go and play in the sheets. So I gave you a VTNA template, how this template works, and in fact, if you go to Jordy's website, he has a video that associates with this template and the paper where he sort of talked about this, and he walks you through how to use it in a practical point. So if you do want to see another way of explaining it through, Jordy's got a great video tutorial on YouTube. How this works is on the bottom here, you have multiple tabs, and for example, I'm going to take the tab here, Order in Product, where I'm ordering A, where I'm looking at product. So the nomenclature he's applied here is he's saying the value in bracket is the concentration profile you were evaluating. So I'm looking at the product trends, and I'm trying to solve the order in A for 2 experiments. Don't pay attention to these. I didn't bother updating them. This is just for reference. This is if you're using it and you had 2 experiments, let's say red versus green, you would go and manipulate these initial values just to have a record of what those are. What you have down here is this value here in time. That time axis is the time axis from your experiment. However you run it, you would say, I am running experiment 1 where these are the time data for specifically experiment 1. Over here, experiment 2 and the time data for experiment 2. Why that's important is you don't necessarily have to have the same sampling frequency between those two experiments. They have an isolated or individual column that's associated with it. So if one of them you were able to sample super, super fast, one you really super slow, no problem. Just make sure you associate that time series with the concentration series that are associated with those two experiments. So here, experiment 1 time, experiment 1 concentration in A, and experiment 1 concentration in product. Those values here, here, and here came from the other data set I gave you. So I gave you these 5 initial experiments, and I've given you experiment 1, experiment 2, experiment 3, experiment 4, and experiment 5. And I've given you a graph plus these initial values. We can come back to those after, but let's take a quick look. If you look at this series, walk me through which binary comparisons do you want to focus on to solve what kind of orders? So 1, 2, 3, 4, 5. You said which two? Entry 1, 2 will allow me to solve power A because B is constant, catalyst is constant. Everybody agree? Cool. So the way you would do this is I run, and by the way, yeah, I built a Copassi model. This is just the data. The time, concentration, concentration, concentration is just what came out of my Copassi model. So this has just been synthesized. That's why you can do the same if you build a model and walk the same path. This is something you can practice. So I took that. What I'm going to do there is I will grab for experiment 1 my time axis right here. So I would just go through. Sorry, it's a lot harder to do without a freaking mouse. There. Copy, go over to my experiment 1, here, paste. That's just your time series. And then, because I'm trying to compare the concentrate, I'm trying to solve for order in A by watching what product does. So my product concentration here, I will grab it. I will associate, I'm talking about experiment 1, so I would paste this into experiment 1. And then back over here, I want my concentration A. Copy, back over here, paste. That's what I do just for experiment 1. So again, it's the time series, the concentration A, and the product. I'm not touching concentration B because I don't care. I'm think of it as the 3 columns are your time axis is what you're measuring, the product axis is your outcome, A is the manipulated variable that you're going to be normalizing against. So those are the 3 pieces you need. You don't have to touch this. The TA, that's your modified time axis. And if you look at the formula associated with it, up here, that is your sum done in, so the equations I showed you last time of what that time axis is, it's just the time multiplied by a Riemann sum of the concentration of A as a running total normalized by some average. So it's got the math that you need to do that squash and stretch of your time axis. So that's already built in. You don't have to touch this. Now we're going to do the same thing for experiment 2. So remember we said we want to compare 1 versus 2. We just took all the stuff we need for experiment 1. I'm going to go over to experiment 2. Once again, grab time axis, go over here to experiment 2, paste. I'm going to go back to experiment 2. I'm going to grab my A axis, copy, and here, paste. And once again, I'm grabbing my product here, and I'm going to paste that in. Okay. Now this value here, this in yellow, that's your order. I'm going to set it back to 0. Remember, when you set this on this graph, if I say I'm comparing experiment 1 to experiment 2, I've set up everything where the times are associated correctly, the concentration A's are associated, and the concentration products are associated. So again, that's like one matrix just for this experiment and one matrix just for this experiment. If I set this equal to 0, I should get, if everything's working properly, this should be my product versus time for those 2 experiments. That's a quick check to make sure it's all set up properly. So visually, If that is product versus time only, and I only manipulated A, what do these two curves tell you? Do you expect to see an order in A or not? I changed only A. Yes. Is it positive or negative? Did it get faster or slower as I increased or decreased concentration A? So it's positive order. That's what we know. So that's, again, you just do this as a gut check to say what direction you're going to do. Now what you can do is, now that this is set up, you go over to this value and you say, okay, it's positive. What is it if I say it's 0.1? No dice. Okay, 0.2. And this is just the boring part of the curve. 0.5. Okay, what about 0.6? Okay, what about 0.7? And really, that's the thing that Finn just went through. He iterated this graph where he's just indexing that value and updating the curve. If I set it equal to 1, you see now data points start to overlap. For most of the time course, starts to deviate a little bit here at the end. So it's a bit of a judgment call, but 1 looks pretty good. What about 1.1? Better? Worse? Who's been to the eye doctor recently? Yeah, everybody, again, I just got new glasses. You know what I'm talking about. Do you like 1 or 2? 1 or 2? 3 or 4? 3? Welcome to the fun of visual overlap. It's easy, not very quantitative, right? Because how do you score which is better? 1 versus 1.1. Or okay, well, let's do this other one. Let's get really nuts. 1.126, numbers. Is that better or worse? You can do this all day. So as a quick question, what do you guys think? What is a way for me to objectively measure or score my overlap?
One possible way is to plot the RMSE versus the
But what's the RMSE of? Like you're saying error versus order, right? But what are you using as a scoring function for your error?
I guess we can use the RMSE for the blue, sorry, the green curve, the red curve.
But again, give me a numerical value. What are you scoring? Like it's not linearity, right? Because these may yet be curved, right? If we go back to something like this, that is a good overlay, but it's not linear. Those points are in between each other, so they're interspersed. I would say that this is a good value, but I can't say go fit it to a straight line and plot the r squared for linearity. That's not appropriate. I need to know the function that they're representing. Yeah?
Could you create a logarithmic trend line for the product against your x-axis and then compare whatever function describes your red markers there to that?
So it sounds like, yeah, I think I know what you mean. What you're trying to do is to take a nonlinear curve, use a logarithmic axis to kind of linearize it, and then try to fit against them a little bit.
Not necessarily linearize it, more create a logarithmic function and compare one function against another.
And yeah, and there's varieties of that version. Maybe we could take like an ODE type fit and say, give me any function that fits through these points, or a log function. The good side about that is, yeah, you have a mathematical descriptor of what these data points are and how they may compare to each other. The downside, like we talked about last class, adding things like log disproportionately squashes and stretches error, so it can false hope is the thing that you may build in. It's not wrong, but the thing you have to watch for is that may lead you astray just because the error gets blown up in certain parts of how you do your functional manipulation. Agree. What else? What about distance? No, this is what we use in Kindle-Lite. It's not, and again, quick point. There's nothing that is perfect because there are a lot of ways that trip these up. There's actually a paper by a researcher named Professor Mimi He, where she's actually got a version of this where they use a couple of different error functions. The approach we tried was, look, if I were to take every data point and measure the distance between any point and its nearest neighbor, and I basically plot that as a line, and I sum up all the distances, if those points and scatter points, if you imagine red and blue are now one data series, so I actually collapse them into a same trend, and then I just calculate the average distance from any data point to any other data point, I don't care if they're from red or blue, the best overlap should be one where the clouds are at least clustered visually, right? It was an optical kind of a feature. It will fool you in certain cases, but that's what's going on when Kindle-Lite scores it, is it's just saying, I will take two data series, red and blue, I'm going to put them on the same function, the same axis, right? I'll squish them together, and then I'm just going to measure the distance between any points, and I'm just trying to keep varying my order value until that distance value gets smallest. It's not perfect, but that gives you one. But anyway, back to our point here. Usually what people will end up having to do is kind of make an arbitrary call. And the part I want to focus on is 1 is not bad. And if we do something like 1.1, also not bad. The way you should really approach this, or use the best rule of thumb I'd say for VTNA, chunk things out. Is it 0? 0 is pretty obvious. Like, it is definitely 0. Is it fractional but lower than 1? 0.1, 0.2, 0.3, or maybe 0.6, 0.7, 0.8, but it's a range. Anything that's kind of not 0, not 1, but higher and fractional than 1, or lower and fractional than 1, those are relevant. So in other words, something that's kind of in the half to 1 range, you can be pretty sure it's down there, but you don't know the actual number. Half to 1, again, pretty sure that it's in that range, definitely not 1, or slightly bigger than 1. In this case, this is a case where 1 and slightly larger than 1 seems to fit, right, is how I would do. Point is, this is not a single value. It's kind of an arbitrary Gaussian around what the number fits, because this is perfect data too. I'm showing you individual concentrations created by capacity. If you put error on top of this from sampling, it gets even more loose, right? So don't use VTNA as oh yeah, I found a reaction that's 1.6 and I'm going to go right to science because I found a reaction with 1.6. No, there's a lot of squishiness about it. It's not analytical in that same way. Okay, that's the first one. Let's go back to our data. I think it's about first in A. Cool. How do you get order in B based on the data that you've been provided?
Compare 1 and 3.
1 and 3?
If we know the order already.
Yeah, that's reasonable. So, like again, what's the problem you guys see? You identified it. Is there a nice clean part of this data set where you can do the same 1 versus 2, I'm changing one, not the other, right? The data set you've been given, you don't have that luxury where there's A didn't change and B did, right? There's always one out. This is a reality of when you try to run something, this may happen, right? There may not be a way to hit that value. So, I agree. A compromise is 1 versus 3 will at least help me to interrogate B as long as I'm confident that the order in A is 1. That's a reasonable approach. Okay, so we can do the same. I will go through. Now I'm going to take the time course for experiment 1, and I'm going to go back to my data set. If you look down here, I now need order in B using product. And that's why this designation here, I've actually added these in because this is order in product using experiment 1 to experiment 3 from the data set I gave you. This is order in product experiment 2 versus experiment 3. I've added these other ones in there to give you some way to play. I've just duplicated the sheet so you can manipulate it. Okay, so in that pairwise one, I want you guys to take a bit of time, 10 minutes. Go finish this set. I just gave you the sheet. I've given you the values. Do your copy and paste. Tell me what you think order in B is and order in catalyst is based on the series that you've got. 3 here. Okay, let me dive back into this now. So I want to just quickly, so what I just did, I just recopied it. Again, remember, I'm recording the screen points, so if you want to go back and watch the individual manipulations, you can go check the video from the class, and you can see the sort of clicks and pastes I'm doing just to help us reference. So I was using experiment 1, and I'm using time, product, and since this time I'm trying to solve for B, I'm using the B concentration one to pop into my B curve here. Same thing for experiment 3. So I've just populated those in. Once again, I've set my order in B to 0. If you look at your time curve there, what does that tell you? What's your expectation from this? Did changing the concentration of B have a meaningful impact in the rate? No. So order in B is probably 0, right? Like that sort of fits. Now, the interesting thing, if you go back to your series here, though, 2 versus 3, you could kind of do the same thing, right? I've got A, where I've got a high concentration, low concentration value. I know that's going to be first order. This also doubled up. If you actually check that one, or check other series, if you choose other pairings where there's multiple things changing and you only compensate for one, it's not going to make sense when you actually go and plot it. Like if I only took concentration 2 and reaction 2 and reaction 3, where I populated the concentration of B and product from reaction 2 and the concentration of B and product from reaction 3, remember, this one sheet is only normalizing for single concentration and responding product. That's an experiment where the concentration A is massively different. It's not going to make sense on this graph. Any changes I'm seeing is because it's a convolution of potentially both. So some of it is you have to choose the right binary experiment and put them in. But let's go back to the actual time, just the full time course curve. If you look at experiment 1, it runs similar initial concentrations, gets you to product. But look closely at this. This is a reaction, and again, I made it in Copassi. It's something like AB and catalyst. If you look at this curve, does it look like mass balance is held? Right? If I summed every single data point up, that's flag 1. Something seems weird, right? Because if I add every single data point, something doesn't seem to be showing up here, right? Just ask the question of the other point. What do you think, like what's going on from 40,000 seconds to 60,000 seconds? I have starting material. Am I making any more product? What's going on? Everybody has run an experiment that looked like this. What do you blame it on? Side reactivity, or you ran it with the catalyst. What happened to the catalyst? It's dead, right? This is a case, visually, if you have an experiment that comes out like this, again, I'm not saying it's inappropriate to do the VTNA. Early in the reaction, those early data points are probably clean. But if you start making decisions about those late data points, there's a case where it's got all the fuel, has A and B, it's not making any more product. That's a problem. Probably catalyst is dying, which means anything we try to pull out in terms of order and catalyst will be suspect because catalyst concentration can't be constant given what this thing's telling us. If it doesn't go to 100%, catalyst concentration has to be decreasing somehow. That has to be something you're going to have to add in. Yes?
Are there any problems associated with changing the limiting reagent?
No, not with VTNA. Like that doesn't matter which is limiting or not. No, that won't hurt it at all. It doesn't matter which one is limiting. The curves may get a little bit more skewed, but it's something you can practice and play with. It won't impact this sort of outcome unless it's a saturation behavior that we discussed in last classes, right? If changing the limiting reagent will suddenly hide something because it's now super high in concentration of something that is now going to be saturating, you may see an impact, but it's the same thing as like this. It's basically relative concentration problems. There's nothing implicit based on which is limiting, though. Okay, point one. Visually, it looks like catalyst is deactivating, probably. Look at your two starting materials, though. We said mass balance doesn't match up, but there's another clue in there, too. What's going on?
The starting material that starts higher in concentration somehow ends up lower in concentration.
Red's decreasing somehow.
Yeah.
Red's going somewhere that's not product. So there's a deactivation pathway which seems to be tied to the red stuff, too. Those are meaningful, right? These are clues of what's happening in the actual system. This is a case, what I've built here is an example where your mechanism here must include a deactivation pathway, so your catalyst is decreasing over time. And this is telling you that, well, whatever the decomposition is, might be associated with the thing that's missing. Red started high and ends up lower. Well, it's going somewhere, which means there's a species you haven't accounted for, which might be your poison, right? That might be the thing that's actually killing. These are sort of the other subtle pieces of, reactions are constantly whispering to you. You just don't know if you're listening to it well enough. These are the features that you can pick out. These are not part of ETNA. These are sort of the normal time course things that you have to put in, but it means that one flag you should see from this, if mass balance doesn't line up, the values you're getting in your VTNA should come with a big asterisk. VTNA and all these other sort of rate methods, these order methods, assume that it's well behaved and there's no deactivation. Right? So this is something where you could report this and say, it appears to be first order in A and zero order in B, asterisk, 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 I have unaccounted mass, something else is happening here that may be part of why this reaction doesn't go to completion. Right? Those are the kinds of other features that you pull up. So in that case, if you're dealing with a system, what I've been telling you about is what we call different excess experiments. Remember, different excess means you're changing the initial concentration difference between two species. A starts at some concentration, B is held constant. The difference between those two initial concentrations is the thing I'm varying. What we have is another one in the toolkit called a same excess experiment. Now think of this as, if I am a reaction, in this case this is a Suzuki reaction, lo and behold, we keep coming back to these beautiful guys. I'm going to start an experiment where I have some amount of my two starting materials and some amount of catalyst. And I'm going to run the reaction and it looks like this. So not only is it not going to completion, I seem to have, it seems to be slowing down. If I try to fit this, it doesn't fit like a normal first order. This is kind of the outcome I get from running one experiment. Over here, this is a duplicate experiment. I ran two experiments, and what I can see from this one is my system is well behaved. It is not, the difference in mass and difference in concentration is not because I screwed something up. I can trust my data. I can at least do the same thing twice. That's what the bottom left-hand corner is showing you. What's missing in this one is, if you now imagine, I'm starting with a case where I have, let's say, 0.1 molar in A, 0.1 molar in B, and some amount of catalyst. So the difference between those two, what I call the difference between A and B, it's 0 at this moment, right? I have equal concentrations of both. If I take both the concentrations and drop them by the same amount, and I hold my catalyst concentration constant, it's like I'm doing a higher catalyst loading, right? So what I do there is I run this other experiment where I drop both concentrations down, and I get this little guy down here. Dropping the initial concentration of both species, I get less data. It still goes to the same degree of conversion. But if you notice this graph here, the slope initially is much sharper than either that slope or anything along this curve. It looks like it's running really fast. And you can think about it and say, well, yeah, you have more catalyst there. That seems constant. But think about these two curves if you think about these two curves in sort of a personified way, the filled lines is like taking, let's say, 10 mol% catalyst. Well, no, let's use real concentrations. 1 millimolar in catalyst, 0.1 molar in both materials. So I've got all this starting material and a little bit of catalyst. And the catalyst starts and it's running around the cycle. It's going around and around and around and around. At some point, I'm using up starting material and I reach this concentration right here. This concentration, if I use up this amount, this data point right here represents the same experiment if I started off fresh. So if you think of it like a relay, I start one experiment with some amount of catalyst, and I have it ripping around the track. And it's burning starting material. And I start another experiment, same amount of catalyst, same concentration of catalyst, but it's fresh. And I started that lower amount of starting material. What I'm competing there in that moment is how fast is a reaction at some set amount of catalyst with less starting material, It's like a later time point in the reaction compared to same amount of catalyst, but it had to arrive to that concentration of starting material. So I'm basically checking how does this catalyst stand up after many, many, many cycles. And there's two things you're probing. As the reaction runs, I'm making product. So if the reaction builds up product and product hurts it, after many cycles, yeah, my two initial concentrations of my starting material, the fresh versus the other, those are the same. But if they run at different rates, product may be an inhibitor. Right? So if I imagine I'm dropping to a certain concentration versus I'm starting at that concentration with the exact same amount of catalyst between those two, the main difference from dropping is I've made up product. Product is now present and it might be an inhibitor. The other is just time. If it's going around cycles and every time it goes around a cycle, something could decompose, it's burning itself out. It's reaching oxygen or whatever. There's maybe a decomposition not associated with the product. But that one example, you have those two. So the way we compare it is we do what's called a time shift. I take these two and I simply slide that data point over and I say I find a concentration of product where those two curves align. And all I'm saying is concentration that has been running to this point gets slower, fresh catalyst runs faster, something is inhibiting that the longer reaction, the first one I did. Now you can start playing this game of, well, is it just dying because it's dying? Or I can add in the product. In this case, this reaction also produces this halide salt. When you're doing this turnover, bromide, we don't show it here, but potassium bromide is part of the product that comes out. So if we actually take this same system, I redo this lower concentration, and I just dose in a certain amount of kBr, I get those two curves to overlap with each other. I can now start at the lower concentration, same amount of catalyst, plus my product, and those two products line up with each other. I have now found that it's not because the palladium is dying, it's that that second reaction does not have this potassium bromide in there. If you're building up potassium bromide, it's inhibiting the reaction, right? Yeah?
Is that published?
Yes. Oh, I'll give you the reference. Sorry. This is Christie's one. This is where it all comes from. This is the big one you want to go and look at. Donna came up with this method. We published it in Jack's, I don't remember the year, apologies. This was this idea of time shift analysis. I can start with two experiments and I can actually slide those two over, and the time adjusted profile, if they overlap, there's no deactivation, there's no inhibition. And you have this pattern-wise recognition of if the time shifted profile runs faster than the one that's turning over, you have some inhibition. Then the next follow-up experiment you do is a product addition experiment to that lower one to say, did product hurt or not? So it's that 3 binary experiment that can help you to suss out. Because what I've seen in this one too, this is an example where you see this happening, oh, my reaction's not going to completion, maybe I have to dry my solvent more. And you go through like 3 months of creating an amazing THF still, and it looks the same. Oh, maybe it's my oxygen, so you create a glass bomb that you seal, and it looks the same. Nobody checked if product was hurting you. I've seen graduate students go through months of trying to improve their ability to run this reaction, and there was never a chance because the product was always inhibiting it from the start. This would save you all that time, right? Any questions on that? Okay, that's all we're going to talk about today. Again, I have those curves and stuff you do. I'd encourage you guys to go and practice with the VTNA template. I'm going to give you guys over the weekend an assignment to work through for the next week, which will ask you to work through some data, including some of the data sets of other publications that we've done for my lab applying VTNA. All right, guys, I'll see you Monday.